Hello everyone, this is ELE 3037, third session in which we are going to discuss about the remaining topics of noise theory. So first we will discuss about what noise ratio is. So the receiver noise ratio is the ratio by which the input signal to noise ratio deteriorates during a noisy receiver circuit. So imagine if we have, let me turn on my tab here. So if imagine we have an antenna that receives a signal here at this point, then a system will have its own noise and this system will also have a signal. So if I take the ratio between the signal to noise here and after a cascaded receiver signal, which is not purely what antenna is but a little bit different, it may have amplifiers and filters and other circuits that we will discuss later and during this course, then there will be a different signal to noise ratio here. So this is, you can say, the input signal to noise ratio to this receiver circuit, or you can call it black box, and here is the output. So if we have the ratio of signal to noise ratio at the input side with the output side, then we will have, we normally call it a noise ratio. Let's go to an example. Suppose signal to noise ratio is equal to 25 dB at the input of an amplifier whose noise figure is 10 dB. Then the signal to noise ratio at the amplifier output will be, noise figure is, there's another important information here, that noise figure in dB is actually noise ratio in linear. So noise ratio is actually dB equivalent of noise figure and vice versa. So noise ratio here would be 10 log of signal to noise ratio at the input or signal to noise ratio at the output. If we take the logarithmic formation, then it would be 25 dB minus the signal to noise ratio at the output side, that is 10 dB, as we get in the in our example. It will give us signal to noise ratio, the noise ratio of 15 dB. Note that noise figure is decibel equivalent of noise ratio. So that is one important information that we should emphasize on. So the next topic is noise temperature. The amount of noise added by a noisy receiver can also be expressed in terms of equivalent temperature TE applied at the input of the system. So imagine same example that we have seen in last slide. Sorry, let me turn on my pointer. Okay, imagine we have a receiver that is kind of black box. It can have one component or multiple components, we don't know. So if there's a signal coming in and then a signal going out, the signal to noise ratio here is input and signal to noise ratio here is at the output. So what this receiver does, it adds a noise that is equivalent to a noise that it will have if there is a noise source placed at this point. Let me try to explain it with a figure in coming slide. But first, just imagine that if we have a signal at the input and noise at the input, that signal at the output will be amplified, but you will see that noise should also need to be amplified. Imagine if this is a simple amplifier with a gain G, then the noise will also face a gain while signal will face a gain. That is pretty well known. The available noise power at the device input is generally N in is equal to K T naught B, where T naught is a reference temperature in Kelvin. The available noise power at the device output is N D out is equal to G K T E B. So in this system at this stage we have N in is equal to K T naught B, while this device will have a gain and an equivalent noise temperature TE that this device will add into our final output. So the ND out will be equal to G K T E B. T E B, not T not B. So there's another way of looking at the noise temperature or equivalent noise temperature. So consider these two diagrams. On the right side, you will see that there's a resistor of 50 ohm and an ideal temperature, you can say an ideal temperature 290 Kelvin, and this resistance is creating a noise. So we have a real DUT here that is device under test, or it can be a receiver or an amplifier that will have a gain value. So if we want to see what exactly we will get in at the output, then we will get two components of this receiver. One is this noise being amplified by this gain plus the noise that is a part of this receiver. So if I want to see what this noise created by this receiver is exactly, then what I will do, I can consider that I have another receiver which is ideal, giving me no noise at all. So what if I increase the temperature of this receiver from T to TE, or you can say ideal to TE? Then there will be a noise created here, a little bit of noise created here. If I add this TE into the temperature here, that is a non-ideal temperature, then I can consider my DUT as completely noiseless. So it will only have G value. So this T is important. It's called equivalent noise temperature. So noise generated at the output of a device under test has two components: the amplified thermal noise from the input resistor that we have seen here, this one, and the noise generated by DUT itself, that is this noise by DUT. The real DUT is modeled as noiseless equivalent device for which all internal noise sources has been removed. So we pushed that noise from this DUT and placed it here in the form of our equivalent noise temperature. This is combined with an additional thermal noise source TE at the input. TE is equivalent noise temperature of the device under test or any receiver. So this kind of method is actually very useful when we have uh, a high frequency system that do not contain one system or one equipment. Just imagine if we have a simple amplifier, then the data sheet of this amplifier will actually give us the information about what exactly is the noise of this amplifier is. But just imagine if our device is a combination of multiple amplifiers and multiple resistances and different high frequency devices plus a few diodes that are connected to another uh, uh, current source, then we will not be able to get to the exact output. So what we normally do, we just place this whole system into a black box and calculate what exact TE is, and then consider that TE as equivalent noise temperature, and we are only then worried about what gain value this system will give us. The total output noise is the sum of noise powers, and total is actually amplified source noise plus device output noise. So the device output noise is the noise that has been created inside this device. So if we write it in the form of gain, then G and in plus and D out. We have already seen what N D out is. So N in is K T naught B. T naught is the temperature reference temperature, and G K T E. T E is the equivalent noise temperature B. So from this we are going to get to an equation that is GK T naught plus TEB. So imagine we have one source with noise temperature T naught. The input noise to this system will then be KT naught B. This system has its own gain. This system has its own TE. So the N total will be GKTEB plus GKT naught B, which is what we have seen here. In terms of noise ratio, NR, as we have seen before and did one example, signal to noise ratio at the input and signal to noise ratio at output, if we take their ratio, then we will get to noise ratio. Or noise ratio can also be written as power at the input of a system or a receiver or amplifier divided by the input noise overall divided by P out, that is the power at the output of the receiver, divided by N total out. So P in and in, here P out and N total out. You see, this N total is actually a combination of noise that has been amplified, input noise has been amplified, plus the receiver's own noise. So P out is equal to G P in. So noise ratio, if we do a little bit of maths, then we will end up in this equation, that is N total out over G N in. So from here we can get to the point where if we write about N total out, it's GKT naught plus TE into B divided by GKT naught B, and if we cancel GK and B, then we are going to get this result, that is 1 plus TE equivalent noise temperature over reference temperature, where G is the device gain, T is equivalent noise temperature, and T naught is the reference temperature. Generally it is taken as 290 Kelvin, but it's up to an engineer whatever reference temperature engineer feels like selecting. So the convention between the conversion between noise ratio and equivalent noise temperature is given by TE is equal to T naught NR minus 1. That is kind of if you do a little bit of maths from the equation that we have formulated in the last slide, you will get to this result. The lower the equivalent noise temperature is, the better the quality of a receiver. Essentially, TE represents noise power present at the input of a device plus the noise added internally. Noise temperature measurements are necessary because both to characterize components and to check the results of circuit design. Methods are chosen in which the bandwidth and or gain do not affect the measurement, as these parameters cannot be known with sufficient accuracy. So again, from the previous example, if we have a simple amplifier, then we will generally know what G is, what TE is. But if we have a complex system of multiple cascaded amplifiers and a biasing network, then this whole system, it will be very difficult to actually identify what exact accurate bandwidth it supports and what exact gain it is giving. So sometimes it is very difficult to mathematically identify how much noise will it create. So that's why noise temperature measurements are used. The simplest technique of measuring noise temperature of a device is the hot and cold method, whereby the input noise temperature is compared for a cold noise source and for a hot noise source. So that's one method that is generally used for to identify the noise temperature in any high frequency system. Usually, for simplicity, one of these sources is at standard temperature T naught, sometimes 270 Kelvin, and the other is then heated or cooled. The device under test can either be simple component or complete receiver, that we have already seen. So noise temperature measurement. Noise temperature measurement techniques are based on supplying a known amount of excess noise to an RF input of a receiver and then measuring the change in the noise output level. So to define, let's first define a few terms. T system is the system noise temperature. Trx is the receiver noise temperature to be measured. T on is the noise source temperature when input noise is turned on, and T off is the noise source temperature when it is switched off. So noise source on will give us overall T system is equal to Trx plus T on, and when the source is off, then T system is actually Trx plus T off. By comparing these two, we will be able to get to Trx because we have an equation with two equations with one unknown variable. One can be identified and the other can be calculated from that. The noise power from the receiver is proportional to the system noise temperature. So on and off power ratio Y is given by Tsys over Tsys prime is equal to Trx plus T on divided by Trx plus T off. So if T on and T off are known, Y can be measured and Trx can be calculated then using the same equation that we have seen before for noise source on or noise source off. So Trx actually is T on minus Y T off divided by Y minus 1. So you don't need it to be that much complicated. If you actually get Y, then you know how to put these equations and get to the Trx. So the hot cold method uses the thermal noise from a matched impedance resistor, normally 50 ohm, for a communication receiver at two known physical temperatures. This method gives the closest result to fundamental measurement noise temperature. So here we can see that noise from a matched impedance resistor. So what actually happens is, imagine we have a receiver in which we have one amplifier or anything different, and then we are just connecting it to a scope. We will just have one resistance connected to it. So the noise that is created by this resistance is actually kind of input noise for this receiver, and the total output noise will be equal to the amplified noise Ni plus its own noise, this receiver's own noise. So by changing the temperature of this resistance to 2 points, we can actually identify the equivalent noise temperature of the device. For best accuracy, a large difference in the temperature is necessary. To present an accurate 50 ohm termination at both temperatures, the resistance must have good RF characters and a low temperature coefficient. So this resistor needs to be a good resistor, a very accurate, highly accurate resistor, so that the temperature of resistor is changed, then it can easily translate into into the input noise for the receiver. So what happens is we have two temperatures. I will go back to red. If we two temperatures, we will first put this resistance in one temperature and identify exactly here what exact output we are getting, and then we are going to push this same resistance into another temperature, and then we are going to have another output. So we are just going to compare those two outputs, and from the equation that we have done before, we are going to calculate our variable y, and by calculating a variable y, we will be able to get to the T receive or Trx. So yeah, that's how it's done. We have a broadband coaxial switch, or we sometimes for standard or very general devices, we do not even need broadband coaxial switch if our bandwidth is reasonable enough, then a standard resistance of a very good RF quality, a very good quality at RF frequencies, we will be able to actually get to the to the answer of the RX without requiring a broadband coaxial switch. Our next topic is Friis formula. We also call it Friis transmission formula. So we have seen in previous slides that if we have a single receiver, then it will definitely have an input noise, and then the output noise will be actually total output noise, which will carry the noise that is created by this receiver plus the amplified noise, that is this one. So here we will get a combination of both of them. So imagine we have a system like the one we normally see in our houses, in which there is one antenna placed on a rooftop, and then there is a mast head, and then there is sometime an amplifier, and then there is another converter or another amplifier at another location around the house. Or imagine if we have two-way power splitter, and then another two-way power splitter, and then we have multiple amplifiers placed all over the house just to amplify the received signal that we have seen from the antenna. Then the system will not look like a very simple single stage system like this one. The system will look like we have one high frequency system, and then another high frequency system, and then another high frequency system, and so on. And sometime we just need to have two or three, and everything will be fine from that point onward. So imagine if we have an input noise of a signal, that is of the resistance or a device that is attached to this receiver side. Now it will have its own output, which is a combination of this receiver's noise and an amplified NI. Now the second receiver will have its own noise, that is, you can say N2, we'll just consider it N1, N2, N3, and then it will also have an amplified version of this output, that is N1 out, and N2 out will be input of N3. So it will also have its own noise, plus it will amplify whatever it is getting from the output of previous high frequency system. So the system gets a little bit complicated. So Friis formula kind of solves this problem. So in a communication system, several linear devices are often cascaded together to form an overall system. In the receiver system, these devices may be our pre-amplifier connected to a transmission line that feed a down converter, and IF amplifier. IF means intermediate frequency. The system performance, the overall power gain G, and the overall noise characterization needs to be calculated. So this is an example of a cascaded system in which device 1 has G1 TE1, device 2 has G2 TE2, and so on. So this at this start point we have a noise temperature Ti and an I, that is noise because of that Ti. So as we move along our cascaded system, then we will have multiple gains, and for example at the output of my first amplifier or device 1, I will have this device's own noise plus the noise that it has amplified. At device 2 level, I will have its own noise plus noise at this point, and so on. So if we have 4 devices, so let's consider a simple example in which we have 2 cascaded amplifiers, and we are assuming that their impedance is matched. While that's not the case in reality, you will definitely see an impedance mismatch at these points, but that is part of second term of the same course. You will be able to understand what exactly impedance matching is and how we can match multiple devices. So now just ignoring the impedance matching and assuming that all the impedances are matched with each other. So let's see what happens if two devices are cascaded and what will we get at here if we have gain of device 1 is G1, then the equivalent noise temperature is TE1 and the noise is N1. For the second device we have same with subscript of 2. So the overall amplifier gain G is actually G1 multiplied by G2. That's pretty well known and it's pretty obvious. While the overall noise temperature needs further thought, because we know device 1 will add its own temperature plus it will amplify the noise that is coming in as an input. So examining the input to second amplifier, combine the source input temperature and first stage temperature as Ti1. So Ti1 is the output at the output of the first amplifier. It will be equal to G1, that is the gain of first amplifier, into Ti plus Te, T equivalent 1, that is its own equivalent noise temperature. Then the thermal noise at the output of to the complete two-stage amplifier and not that is going that we are going to express in form of equation now. Amplifier source noise is equal to source noise amplified by two amplifiers, so it's G1 G2 and input is equal to G1 G2 K T I B. So Ti is actually the input noise temperature. So excess noise from first stage amplified by second stage will be equal to G2 and 1 is equal to G1 G2 KTE1B here. That's important to note that it's TE1B. This one. Yeah. So excess noise from second stage would be N2 is equal to G2, because we are now looking at the amplification from a second amplifier only, into KTE2B, that is now input of to the second amplifier rather than general T. Adding together N naught is actually a combination of G1 G2 KTIB plus G1 G2 KTE1B plus G2 KTE2B. So TE2 is the equivalent noise temperature at the output of second amplifier, this is the output of first amplifier, and this is actually what we input. For cascade amplifier, the thermal noise N naught is equal to GKTI plus TEB. Overall system has parameters GTEB. Check back the diagram, or we can just quickly make diagram here. TI, G1, TE1, TI1, G2, TE2, and TI2. Ti1 is here. So yeah, so the overall amplifier gain G is equal to G1 into G2. So Te is actually equal to Te1 plus Te2, and noise ratio as we have derived is actually Nr1 plus Nr2 minus 1. So if we generalize this form after doing some maths in this two amplifier cascaded system, then we will end up in equation like Te, the equivalent noise temperature at the output of a cascaded system, is actually Te1 plus Te2 over G1 plus Te3 over G1 G2 plus Te4 plus G1 G2 G3 and so on. Similarly, the noise ratio would be actually Nr1 plus Nr2 minus 1 over G1 plus Nr3 minus 1 over G1 G2 plus Nr4 minus 1 and G1 G2 G3 and so on. So this equation is actually very important equation and it's called Friis formula. So in say similar examples in which we have multiple cascade systems like this one and this one and this one and this one, then what we normally do, we consider it as a standard cascade system, and using Friis transmission equation we can actually identify how much equivalent noise temperature we are going to get at the output of this point, when the gain of these devices and the noise temperature of these devices is known by the datasheet. Note: when making calculation using Friis formula, decibel should not be used. Noise figure and gain should be converted to power ratio. Each amplifier in the cascaded string of amplifiers produces a certain amount of noise over and above the thermal noise. As the input signal and noise is amplified, the signal becomes strong enough that the small amount of noise generated by successive stages adds relatively little to the overall noise of the system. So just let's see, for example, if we have a very small noise signal and this noise signal is kind of amplified to a certain degree, but in comparison to this noise signal, and let me draw a signal in a better way. Imagine this blue represents a signal and red represents noise, and after the cascade of multiple amplifiers, the signal is so large that sometimes if the noise is added by a cascade system or an amplifier, it will not have any impact, but this will happen at the later stage. So imagine our first device is not good enough and it adds its own noise so much that it kind of is equivalent to the signal, then whatever we will get here will be amplified by this second amplifier and so on. So our signal will be difficult to be decoded at the later stage of the amplifier of the cascade system. Sorry. From Friis formula, it can be seen that the first stage controls the noise performance of the whole amplifier chain. This is true even if stage 1 has lower noise ratio, because after the first stage the signal is large enough to overpower the noise. This is a general case that happens in almost every receiver that we normally use nowadays. Therefore, in the receiver system design, it is important that first stage is a low noise high gain device so that the noise ratio of the whole system will be as small as possible. So this is general this statement is generally true for all receiver systems, that immediately after our antenna we normally have LNAs, and LNAs stands for low noise amplifier. A lot of companies make very sophisticated low noise amplifiers, and they have very low equivalent noise temperature, but their amplification or their gain is pretty high. So they can actually get a very weak signal from antenna, and they can amplify them without adding a lot of noise into them. So let's see a few examples of Friis formula. Calculate the overall system noise figure for a system where noise figure of first stage is 2 dB and gain is 8 dB. Noise figure of second stage is 6 dB while gain is 12 dB, and noise figure of third stage is 10 dB. So solution, we know that this is a general form of Friis formula. It will go even further if we have, imagine if we have an NF4 and a G3, then this equation would have gone further, but now we only have 3 stages, then we only need this form of equation. So noise ratio is actually 1.58 at first stage. Then putting the values into the system, we will end up in this result 2.14. There's one important thing to know here is the second term will be divided by a very high gain value. So whatever we will receive here will be divided by a higher value, so it will have smaller impact into this noise ratio. Similarly, next stage will be a very high value at the denominator, and the numerator will be a standard value. So this will again be even lower value compared to this first value. So actually for first one or two or three even stages define exactly how much noise you are going to get at the output of the signal. So as we know that noise figure is actually dB equivalent of noise ratio. If you just do 10 log 2.14, it will give you 3.3 dB. So let's look at another example. Determine the signal to noise ratio at the input to the demodulator of a super heterodyne receiver. Super heterodyne receiver. Sorry for my weak pronunciation of this very long word. So we have one antenna and a minus 80 dB input power at the output of the antenna. We have RF1, that is generally a low noise amplifier, then RF2, and then a mixer with a local oscillator, and then intermediate frequency amplifier number 4, and then an amplifier number 5. So we are interested in signal to noise ratio at this point. NF noise figure at first stage is 2 dB, which is pretty low because it should be a low noise amplifier. At stage 2 and 3 we have a noise figure of 6 dB, and at stage 4 and 5 we have noise figure of 18 dB. We have converted everything into linear because it is important to do so. So the gain at first stage is 8 dB, that is high, that is pretty high given the noise figure is a very low value. That's just a conversion in dB scale. The G2 is 12 dB, G3 is minus 6 dB, because G3 is a mixer, and mixer normally do not amplify the signal. They deteriorate the performance of they deteriorate the power of the signal. So G3 is actually 0.25. It means whatever is going inside the mixer will be only 25% will come out from here. So it's pretty lossy device, so we need multiple amplifiers to compensate for that. G4 and 5 is 20 dB. That's exactly what we did at IF4 and IF5. We have increased or enhanced the output of the output signal at the mixer, that is signal at this point. So it's 10 dB, 20 dB enhancement here and 20 dB enhancement here. Now solution. We know Friis general formula for noise ratio. We are just going to put in the values. So NR for the low noise first low noise amplifier, or LNA, will go here, and after that in the denominator we have one value. Here denominator we have multiplication of two value, which will end up in higher higher value at the denominator, which will eventually bring this whole term down. At third stage we have 0.25 multiplied by the gains here. So this stage will actually have low output, low value at denominator. So eventually what will happen, that this whole term will not go down as better as we were expecting for a general amplifier to bring it down, and that's actually because of this 0.25 here. Note how much the mixer conversion loss and noisy IF amplifier increase the system noise figure. So the overall noise figure after the calculations will be 4.6 in linear and 6.6 dB in dB scale. Part 2. If the bandwidth is 5 MHz, find pre-detection signal to noise ratio for the receiver input signal of -80 dBm. So NTH, thermal noise, is -174 dBm plus 10 log B. So we know that the thermal noise of this system will eventually be -107 dBm. So here we have noise, the overall noise at the output, that is N thermal plus noise figure. We have already calculated N thermal. We now know what noise figure is. So actually the output noise is -100.4. So the signal to noise ratio will be -80 minus -100.4 will be 20.4. So S over N will be 20.4, which is pretty good for. So the next topic is minimum discernible signal. Then the minimum discernible signal, MDS, is the smallest value of input power that produces a discernible signal at the output. So here input and output are for a receiver. So let's consider a receiver. So the smallest value of input power that produces a discernible signal at the output. So if I can sense whatever is coming out here, then the signal is called minimum discernible signal. It is considered to be minimum signal that can be detected by a system when the signal power is at MDS level, the receiver output is 3 dB above the noise level. So imagine we have, for a base station antenna, noise level is at -120 dBm. So if I receive a signal that is slightly above than this noise level at a given frequency band, and this is 3 dB above the noise level, then I can consider it as MDS level. So in the advanced receiver system that we normally have these days, if the signal power is exactly at the noise level, even then we are able to get the information out of that signal. For example, imagine that if I have a frequency spectrum and this is my noise floor level, then if my signal is exactly coinciding that one on particular frequencies, then I can actually bring out this signal from the noise using some techniques that are new. The smaller the input power required, the more sensitive the receiver is. So you will see in industrial high frequency systems that low sensitivity receivers are more expensive, and they have more sophisticated technology, and they have better reliability for receiving a signal. So receivers at the base station are these kind of receivers who has MDS, their MDS value is very low and their sensitivity is really high. Let's go to an example. So imagine we have a cascaded power amplifier, low noise amplifier system, in which first amplifier has gain of 10 dB, noise figure of 3 dB, second amplifier has a gain of 6 dB and noise figure of 6 dB. The bandwidth of this cascaded system is 10 megahertz. So first we know that if we want to use Friis formula, then we will not be able to do calculation in terms of noise figure, so we will first convert everything into noise ratio. So we know that noise figure is actually 10 log of noise ratio, and by doing maths we can identify that noise figure for 3 dB is noise ratio of 1.95 and noise ratio of gain of 10 dB is actually 10 in linear scale because of the formula 10 log NR. So now we will use Friis transmission equation, that is NR is equal to NR1 plus NR2 minus 1 over gain of first amplifier. So we will see that the noise figure of 1.995, noise ratio of 1.995 will be added to this second term to get to a overall noise ratio of 2.29. As again you can see that the majority of noise added into the system is by this first amplifier, not by the second amplifier, because second amplifier has this term 10 beneath it. So 2.293 is actually the overall noise ratio, but majority of the noise that is presented in this figure is actually coming from first amplifier, that is this one. So that's why we normally use low noise amplifier at the very first stage. So again, noise figure is 10 log of noise ratio, which is 3.6 dB. Now receiver noise power at the rate of output, or what you can see is whatever you will get here is actually minus 174 dBm. That is the noise floor at room temperature plus 10 log B plus noise figure. So just doing a little bit of math, we will get to this minus 100.4 dBm as output. So receiver output signal for calculation of MDS is actually equals to noise floor plus 3 dB. So our actual noise floor is minus 100.4, so plus 3 dB means if we have a signal of minus 97.4 dBm, then that's enough for us to receive the signal. Hence, since the system gain is 16 dB, the input signal for MDS condition is minus 113.4 dBm. So at this stage, if we get minus 113.4 dBm, given the noise figures and the gain of this system, here we will get minus, if we get minus 97.4 dBm, that's enough for us because this is 3 dB above our noise level. So our minimum discernible signal is this value.